very warm welcome and making us stay very pleasant. Thank you very much. So I will be talking about a problem that we worked on where we looked at finding good locations to place sensors to determine a feedback control. And it's work that was done over years with many people. Here are a list of collaborators, and you will see them in the papers as well. But the application that I will use is motivated by a common interest that we all share, namely the reduction of greenhouse gas emissions. And just in November of 2015, all 3 countries committed to the reduction of greenhouse gas emissions in different ways. For the United States, the energy that buildings use is 40% of all the energy consumption. So there is a significant effort to reduce the energy consumed by buildings. You can see industry is 33%, transportation is 28%, and buildings is roughly 40%. So there was huge incentives to look at how we design buildings to reduce the energy that is being consumed. And in the previous slide, this commitment to reduce energy by greenhouse gas emissions by 26 to 28%, a large part of that is the reduction of buildings, energy that buildings are being used. And that has mainly to do with heating and cooling and light systems. That's what's doing. So the problem that I will be emphasizing on is when we design a heating and cooling system, an air conditioning system, we call it HVAC, heating, ventilating, and cooling systems. So a part of that design has to do with when do we decide to have that system turn on or off, and how should the flow be, how fast, how slow, and what should the temperature be to come out of it. So that's sort of how I want you to think about this little piece that I'm going to talk about. To make another case, just to motivate what the significance is of reducing energy that buildings use, is if one can reduce the energy of buildings by 50%, is equivalent to removing all passenger vehicles off the road in the United States. And I looked up the number, 260 million passenger vehicles in the United States. So it's a significant component. If one can reduce the energy by 70%, then it's equivalent to removing the entire transportation. So it would be trains that have some greenhouse gas emissions, etc. So that's significant. Now it's relatively easy to get reductions in the order of 40% on existing buildings, and I will just show you one example. But to get reduction as high as 70%, one has to use real science, and it will involve new technologies, but then also the things that I talk about, what are smart control designs to make this happen. So an example is the Empire State Building, existing building. They recently made changes to it. So they changed the windows to double pane windows with an argon gas mixture in between to insulate it. They put certain protections on the glass that will keep out UV rays absorbed and also bounce back energy. So the design of windows is a big thing. They look at lights, how it works, so it would activate if somebody walks into a room. You've all seen those kinds of things. And they looked a little bit at the controls on these HVAC systems. So if there are people present, they may sense CO2 somehow and know that they should have it comfortable, while if there's nobody there, it really doesn't matter what the temperature is because somebody cannot sense. So they were able to reduce the energy by 38%. And just to give you a sense, one building, it's 105,000 metric tons of CO2 in a year. But then just to give the scale, the United States in 2013 produced 6,700 million metric tons of greenhouse gas emissions. So it's really a huge problem to address. So as I said, I'm talking about one very, very small aspect in this bigger scheme of things, namely, if I want to design a controller through feedback, so I want to know what the temperature is to decide whether we should turn turn it on and off. If it gets too cold, I want to adjust. So one of the questions is, we do not know what the temperature is at every point in the room. The only thing that we can do is to sense it at a few locations. So the question that I'm talking about is, where should I place my thermostat? I may have one. And from that one reading, decide what's happening in the rest of the room. So that's the constraint, that's the physical constraint. So this is an example of not a smart place where the sensor is placed. So there is a refrigerator that has heat that comes up. There is a coffee machine that makes it hot. And the air intake, how the air circulates, is right next to it. So what I can tell you about this room in the morning when you make your coffee, the air conditioning is blowing full blast because it doesn't know that where you are is freezingly cold because everything that it senses is hot. So the big question is, where do I place this one or two thermostats that I have? Now, the overview of my talk is I'm going to give you an idea of how we look at the problem on a theoretical format, and many of the theory is old and existing and well established. What I would like to emphasize and point out a little bit is the computational challenges that goes hand in hand. So even though we understand the theory very well, when you try to compute, things becomes different. And in this feedback control scenario, I want real-time feedback control. I want to measure what's going on now and change the system, not an hour later, make it happen. So the calculations need to happen very fast. So I will use linear control strategies, and I will point out a little bit why we choose that, even though my problem is non-linear, and Jeff showed how we use linear control in non-linear problems. Non-linear problems in theory is sort of well established, but the computational tools are lacking. So linear control gives us certain advantages. And then I'm going to show us 4 different kinds of measurements. They all give the same solution to the same problem. But the computational cost, what it takes to get that, is very different. So the very basic first problem, and I've been looking at this, is the perfect model. So you imagine we have an inflow vent, and we have an outflow vent in the back. And I want to design a controller that will measure only where we sit. We don't care if it's hot up there. We want to be comfortable. So we want to design a controller that will manage the temperature here using as little energy as possible. Right? So that's the objective. So you can see there's an optimization, there's going to be a cost function. Now what I don't point out here is I'm not going to know the temperature everywhere. So at some point I have to include measurement. Where do I measure? What do I measure? Where do I measure? And how do I use that? But let's pretend that we live in the perfect world and we have full state information. We know where the temperature is. So we can describe the flow in this room by a Navier-Stokes equation where V is the velocity of the flow, P is pressure, T is going to be our temperature, a thermal component that we couple, and we couple the 2 equations, the momentum equation and the thermal equation, through a buoyancy force, hot air vortices. So here we have the temperature that is featured. And then also because of the flow, we have the velocity up against the temperature. So this is a nonlinear coupled system. So what we want to measure is for example, would be the weighted average of the temperature in the region where we sit. So omega W is the location where I would like to make sure everything is comfortable. So our objective is going to be to make our temperature pleasant. And we can agree to R being a desired temperature. So we can decide what we want this temperature to be. And we want to make what we feel as close as possible to that. So we want to minimize J, a quadratic cost function over an infinite time horizon. I integrate from 0 to infinity, making the difference between between what we want the temperature to be and what it is, as small as possible, using as little control as possible. So this U is control, and I did point it out very carefully when I looked at this model. These two terms are a velocity control, how I change what happens up there, perhaps the angle and the speed, and this would be the temperature coming out. So these B's typically reflect an input output. So I want that to be, I want to use as little influence as I can. So what we do is to use distributed parameter control theory. We recast that system of partial differential equations as an abstract differential equation on appropriate Hilbert spaces, because then we have all the existence and uniqueness tools. We have A being the generator of a C0 semigroup and things like that. Then we have all the ammunition to do the theoretical part about existence of solutions. So I would rewrite the problem in this form. A tilde will represent the linear dynamics in the problem. Z will have a velocity component and a temperature component. That would be our state that we are working with. A would reflect the nonlinear dynamics, and B would be the inputs of these controls, velocity and temperature. Our cost function we can then recast. We want to control the temperature. That Z will be a reflection of that, using as little control as possible. Now, for us to use linear control methodology, it is necessary to linearize that problem about a nominal solution. So it could be an equilibrium solution or a target solution. And the idea is that the control U that stabilizes the nonlinear system, we hope would also stabilize, would drive this linear system to zero. Right, so that's sort of the equivalent. So the problem that we are going to work with eventually in the control strategy is how to determine U, when should we turn on and off. I am going to work with this linear problem. So the problem then, if I use a linear quadratic regulator control, it alludes to the fact that I know the state, temperature, and velocity everywhere in this room, which we know is not true. So this is the perfect rule if I have it. So I want to minimize that quadratic cost function subject to a system of partial differential equations. And under very reasonable conditions, if that optimal control exists, it will be an operator, K, bounded feedback operator times the state. So you can see the feedback. It looks at the state and it will adjust the control accordingly. So the things that one needs to calculate to design such a control system is one has to determine what that feedback gain operator K is, because if I have that and I have the state, I have my updated control and I can put it back in the system and read. So K is R inverse the adjoint of B times X, where X is the solution to an operator Riccati equation. It's a nonlinear equation, so you already get the sense that this is a hard equation to address. In this level, its operator is infinite dimensional. And in some cases, for example, if X, the solution to the Riccati equation, has nice properties such as being Hilbert-Schmidt, I have a representation, integral representation of it. So I can write that operator times the state of control, I can represent an integral form. And we are sometimes interested, Jeff mentioned this, we call these kernels functional gains. And we are sometimes interested in not calculating K, but actually calculating these functional gains. And one of the arguments that we can make for it is they are often local in space. They're zero at many places, and then they have value at some places. So one could intuitively argue that when this is large, the regions where it has a lot of support must be regions where the temperature, for example, matters to the controller. So one can think if the functional gain is very large, that may be a good place to control the temperature at. So, right, to put your controls in there. So at some point I will just show you what the functional gains look for this size. On this level I cannot do any calculations, it's infinite dimensional. So one has to discretize the problem using your favorite discretization discretization, finite elements, finite difference, whatever would be best for the problem. And this finite dimension approximation will then look like this. And I just want to point out while I'm on this slide that I not only have the operators A, but I also have adjoints in the Riccati equation. And that sort of becomes important when we choose our discretization scheme, and I will mention a little bit more about that. Now here's a few comments. As I said, I would like to point out computational challenges. These systems are typically extremely large in size, so they now become nonlinear matrix equations, and they are easily even small. For this three-dimensional flow, you can imagine it's very big, but it's in the order of 10 to the 3 to 10 to the 6 easily. And then since they're matrices, we can think of 10 to the 12 unknowns that you have to resolve. The Riccati equation solution has some symmetry properties that makes it useful, but this is a tough nonlinear problem to address. There are many, and it's currently a very active research area, and Chris's collaborator, Benner, has a 2015 paper that still has new breakthroughs in ways to solve this system effectively. And he actually showed in that paper that 3 existing methods give exactly the same iterates, so it seems as if there's something invariant in all these methods, even though they use different things. There are some nice properties that one can try to get, like mesh independence. So if I would use a Newton-type method, Newton-Raphson method, to solve that nonlinear equation, and I make my mesh finer, n gets bigger, then one is afraid that the number of iterations that I need to get convergence might also become big. So you're punished in 2 ways. You have larger matrices and more iterations. If the system is mesh independent, then I can actually show that the number of iterations that I need is independent of the mesh size, which is a very nice. So if you can choose your discretization such that those properties are satisfied, then it is helpful if you use a Newton type of approach. And then Jeff and a graduate student, now he's no longer, he's a faculty, he used to be a graduate student when he did this work, also looked at cases where I don't need the solution of the algebraic Riccati equation, I don't need x, but I need the product of x and a vector. And then they had very creative reduced order modeling strategies to calculate x time a vector as opposed to knowing what x is in particular. So there may be opportunities where one can utilize that. Now what is interesting is that finite element schemes that would work for the problem without control, so if I take the controllers out, schemes that would work, for example, for the flow or the temperature equation, may fail if I want to use it for controlling certain conditions. And the reason is that if my finite dimensional discretization converges to the operators, it does not necessarily mean that the adjoints converge. And I need the adjoints in the algebraic Riccati equation. So sometimes the simulation works great, but the controller doesn't give me the type of convergence that I need. So questions that one asks is, when will I get the right kind of convergence from the feedback gain operator? And properties such as dual convergence, I want to guarantee that both of these things are true, and preservation of exponential stability. Theoretically, we know what those schemes, what additional properties it should have. And I should mention, when we choose discretization schemes for control purposes, I also want to retain control system properties. So controllability and observability, I shouldn't choose a system where that disappears. So one also have to keep that in mind. So those are interesting challenges. Now back to our initial problem. We would like to design a system that can control the flow in this room. We want to decide when the controller will turn on and off. And we want us to be comfortable in the area where we sit. And of course, I'm going to simplify the problem for the first run. So for the results that I'm going to present is in simplified form. This is a nonlinear problem. But if I make the following assumptions, that we neglect the Boussinesq term, so that term where warm air rises, we just ignore that for a moment, and we assume that the fan is always on. And in some instances, that's a reasonable assumption. That's not ideal for sort of devising purpose, but here it will only be a control in the energy equation. So if I make these assumptions, I decouple the velocity equation and the thermal equation. So I can run the Navier-Stokes, solve that first independently. There's no controlling it. And then I can just plug it in here and only look at this equation. So that's a first try to see how one can do things. And so this becomes a linear problem. Velocity is known. So this is going to be our model, and the results are represented for this simple case. Jeff has worked on many other scenarios, and he has interest in restaurants, gymnasiums, a beer cooler in some store. So you should talk to him. There's many other interesting geometries that we did address, but this communicates the ideas. So if I were to have full state and I solve the Navier-Stokes equation, this is sort of what the flows look like. You can see if I would trace the particle, you can see what could potentially happen. I have a bi-quadratic flow inflow profile, so the velocity looks like a parabola. We chose 33 points only in each direction, and that results in 143,000 tetrahedral elements. So just an idea. And the flow is relatively slow, the Reynolds number is 100. Now you'll recall I pointed out that feedback gain operator that we need to calculate the control has an integral representation, that functional gain. And I said sometimes if we can calculate that, that will be useful. Because it tells us that when little k is large, then the temperature in that region really matters. So this is full state information, and you will see the red dot is roughly in the area where we want to control it. So it tells us that what happens, the temperature that's in that area matters. So if we could put a sensor, we should put it up in the area in the middle here. That's what we should do. The physics doesn't allow it right now. There are many different technologies, but our sensor is all mounted. I have to put it somewhere here, right? So there are technologies that will allow different kinds of sensing. Now, if I have sensed information and I no longer know the temperature everywhere, then my previous formulation no longer works because I never allowed sensed information to come in. So a good approach to this, still in the linear format, is linear quadratic Gaussian control. So this formulation takes a measurement y that will be sort of an average temperature measured over an average region. And we will take that measurement and we're going to estimate the state from that and use that in the controller. I will show that on the next slide. But linear quadratic Gaussian control also allows for uncertainty in the model if one wanted to. G times eta will allow for dynamics that wasn't represented in the model, and E times C will allow for measurement errors, for example. So that's sort of the framework of that. So our idea is now going to be, I want to construct a controller. In the past, it was K times the full state Z. Now I don't know what Z is, I only have Y. So I want to use Y to make the controller. And the problem will then look like this. My control is still quadratic cost function. I now have a finite time horizon that should be large enough. In the past, it was infinite horizon. There's our problem, and now you can see that I want to use a state estimate, Z of E, to figure out what the control is, and Y must impact that. And the most simple way to do this is a linear state estimator. So the idea is I determine these operators, A, estimate, and F, input operator. I have my measurement Y. I want to figure out what the state estimate is. Z of E is an approximation for the real state. And once I have that, I will use that to construct the control. So that's the additional part of sensing. And you can imagine that where I get that information, just back here, where I measure Y will have an influence on how good this is. And we want that to be as close to the system as we can. Now to calculate those two operators, the linear dynamics of the state estimate and this input operator F, we have to solve two algebraic Riccati equations. The one from before to calculate k, and then an observer Riccati equation, where q represents the position of where I put the sensor. So for each sensor location, I have to solve an algebraic Riccati equation. I have my operators with appropriate initial conditions, and I have state estimate. Calculate the controller and test the system. So I said there's 4 measures that I'm going to show, and this is the worst one. I just wanted to get it out of the way so that we can all see it. The one would obviously be to find the optimal cost, find the minimum cost. That would be full circle. But it requires a solution to two algebraic Riccati equations, and then you have to solve this coupled system. In other words, we have to integrate this back in time, and we need to do it accurately. So this measure requires then the solution to two algebraic, for each sensor location. You have to solve two algebraic Riccati equations, and you have to integrate the system back in time. So it's simply not efficient. But we did do it. So what we did was we took this wall, and depending on the nodes of the Taylor-Hood elements, we had 225 locations for the sensor, and just brute force calculated for each sensor location to see what was optimal. There wasn't an optimization on that. And it favored the bottom right-hand corner. So this measure, even though very expensive, indicated if in this framework we have to place a sensor, we will do it in 5. A second measure is the minimum error variance. So we believe that if I can make my state estimate, my measurements y is good enough, these two will be close together, so that error will be small. So one can argue I want to determine a location q such that y is good enough to make that as small as possible. And here's just the graphic from calculating the 225 locations, and this is small blue is small, red is big. And we want the error to be small, so this region is a good location. Just pointing back, this measure requires a solution to an algebraic Riccati equation, so that's what we need in this case. So we look at the trace of the solution to the operating Riccati equation. The trace is very easy, but the solution is the problem. So under certain conditions, one can get this input operator to have a representation of this form. Observer functional gain times y. And now I can make the same argument that I made before. Since this gives me a sense of what the feedback of the measurement is in the observer equation, we can argue those areas where this is really large, that would be a good place to place the sensor, because that's how it will feed back into the system. So the next measure is we calculate those observer functional gains, these guys, at 225 locations. And just to give you an idea of what it looks like in 3 dimensions, I'm just going to show you the 4 corners. So in the back, then up here, and then there. So it's very creamy, it's very small, it's at the top left. This is the sensor at the top right. You can see the support is starting to increase. It matters more. It's better if I put the sensor here than there. This is even more at the bottom left, and this is at the bottom right. I'm looking for more information. Okay, so it seems as if that remains a good sensor location. And if I calculate the norm of this functional gain, you can see it's largest in this region. So that is a decent measure. But it requires a solution to the observer Riccati equation, just like before. So for each sensor location, you have to solve an algebraic Riccati equation. But it turns out that in this case, I may be able to use some of these reduced order modeling strategies that Jeff had, because I don't really want the solution to the Riccati equation. I want f times something. So there's a way that I can get that sigma times the function. So we've had some experiments where we use reduced order modeling strategies. We don't care about the solution as much as the projection of that into space. Now this, I will go through this very quickly. I'm going to give it intuitively and just sketch the main ideas. The optimization here is absolutely beautiful. So observability is a control system property that gives me the sense that if I only know what U is, and I only know what figure out what the initial condition was. So is there enough information that I have that I can figure out what's going on? So intuitively think about that. So if the system is exactly observable, so if I have real good measurements, then we say it's exactly observable, right? So now here is the thing. Observability and controllability are two dual problems. The literature writes on controllability. So I want to calculate observability, but from now on I'm going to use the words controllability. So I use controllability just on the dual system. Okay, so all the tools remain the same, it's just the transpose of the matrices that I use. So now I'm going to switch to that. And what I want to calculate is I want the system is exactly observable, it's far away from an unobservable system. It's like a sensitivity that I have. And what we would like to calculate is a placement of the sensors so that the system is as far as possible from an unobservable system. And just to give you an idea what happens now, I'm switching to controllability, but you know it's just a dual problem. This system is exactly controllable, but perturbations as small as 10 to the minus 12 make the system uncontrollable. So checking exact controllability is not smart. What I want to check is how far is it, by how much can I change the system and still remain controllable. So it's a sensitivity kind of idea, this is what is reflected here. So this definition says the minimum perturbations so that the controllable system becomes uncontrollable. Now this is not very useful for calculations, so there was a singular value type representation of it that says the minimum n singular value of this matrix over all complex numbers lambda. This is a tough optimization problem. It's in two variables, it's a global optimization problem, and it's not convex. Here is just for a simple example, you can see there are 5 system of matrices, there are 5 local minima, and you know that's not an easy problem to solve. So the format that it is very challenging. And there is a vast literature of ways that we can try to solve this problem, and each one has their issues. I don't know if it's a global minimum, especially when the system is close to being uncontrollable, it's when these algorithms typically fail. When it matters the most, they fail. So that was a hard problem until 1999, when there was a breakthrough theorem, and I'll just give you the idea of it. This result allowed you to compare two values to the distance to uncontrollability. So it either tells you whether it's larger than or smaller than. And if you hear that, you know we want to use bisection theorem, because you can see how we can try to pin the value. So that's indeed what happened. There was, you choose a value, you test which one of these are true. If one holds, if it's larger than, you make it smaller. If it's this one that holds, then you stop. Okay. And you can calculate the distance to uncontrollability up to a factor 2. There were other algorithms where this is the lower and upper bound of the distance to controllability that you can do to any accuracy. Now this looks fairly innocent until you see what you need to check that. So it looks something like choose a delta, check, and then you close. So it involves eigenvalue problems, just very quickly. The first equation, extract the real eigenvalues of the matrix of size 2n squared. You remember we're talking about matrices of size 10 to the 6 and larger. And compute all purely imaginary eigenvalues of the matrix of size 2n for each group. So it's doable, but not ideal for all the reasons. And then Mengi made some breakthrough work. He also used the projection idea that instead of solving the eigenvalues, he used Sylvester equation tools to calculate this inverse projection. So that was very effective. So now we are coming in a reasonable range. And I'm going to use these algorithms to calculate the positions just to show you what happened. So the distance to unobservability, how far I am from another system that is not observable, is these colors. And I want it to be as big as possible. And it is in that sort of right-hand region. So that would be a full measure. But as you saw that these computational tools was not very efficient, it's still very large. So I'm going to give you the ideas. There's a bunch of slides, but I'm going to give you the ideas of what's coming and just. So people would always ask, what about semi-definite programming techniques? Can I recast that problem and use linear matrix inequalities? And because the solution tools, interior point methods, are very efficient, so can I use different tools to solve the same problem? And there are two algorithms in the literature where they did do that, using many different, very different tools to come to that. So I'm just going to show you that. And the bottom line is those two suggestions work very well for small matrices until you start with a PDE and the world comes tumbling down. So just because it's so beautiful, the very different tools, I want to show that very briefly. So the question is, can I recast that problem in a format like this, where I have a linear matrix inequality constraint, where this reflects positive semi-definites? And the idea is why people ask about that is there's very efficient interior point methods to use that, right? So the algorithm is hard. So the one piece in the literature, it's a Japanese author, used KYP lemma, DG scaling, and Lagrange duality theory to formulate it. And the order of the problem is still 6.5, so it didn't really relieve anything. But I'm just going to show you the primal problem and the dual problem. So this is what it looks like. So you reformulated it using control system tools to recast. The next one was very interesting, sum of squares. So they took the singular value problem, write it as an eigenvalue problem. These two formulations are equivalent. Now the notion of distance to uncontrollability determines find the maximum tau for which this system will remain positive semi-definite. So it's a polynomial equation. So what they did was they looked only at these matrices that are sum of squares, and so they approximated this. So the idea is I only look at those that can be written as a product of matrices, because there are very efficient tools to solve that types of problems. And in the end, using a Gram matrix parametrization, which I had to go and get a K-theory book or something like that to go and look exactly what it means, you can see that the problem just becomes this. I just have to check the positive semi-definiteness of this matrix, but you can see the size is absolutely accurate. Very briefly, the results. The initial approximation, the sum of squares approximation was for benchmark, small benchmark example, successful 35 out of 38 times. The one that used control systems theory, never, only in 50% of the cases did it succeed. And when we tried PDE, no success. So yes, those algorithms exist for nice problems. So just to summarize very briefly, the four metrics are very different computationally, but in this very simple problem, they all indicate the same location. The semi-definite programming and linear matrix inequality methods seems to work terrifically in small cases, but doesn't seem feasible what everyone thought for PDE types of problems. And then, of course, I showed you the very simple problem how you have to make it more realistic, buildings with many rooms, people, etc. Thank you very much for your time.
Any questions, comments?
Thank you.